at the demon drop problem. Took this after an amusement park ride at an amusement park that I used to visit when I was a kid. The diagram shows the top view of a 65-kilogram student over here at point A on an amusement park ride. The ride spins a student in a horizontal circle of radius 2.5 meters at a constant speed of 8.6 meters per second. While that's happening, the floor is lowered and the student remains against the wall without falling to the floor. There's no floor there, but the student remains against the wall. First off, draw the direction of the centripetal acceleration of the student on the diagram. Centripetal acceleration, center seeking, nice, easy, toward the center of the circle. There we go for that part. Now for part 2, determine the centripetal acceleration of the student and the centripetal force acting on the student. Well, centripetal acceleration is v squared over r, so that's just going to be 8.6 meters per second squared divided by, our radius is 2.5 meters, which will be 29.6 meters per second squared. And if we want the centripetal force is going to be MAC, which is 65 kilograms, times our centripetal acceleration, 29.6 meters per second squared, or 1924 newtons. Some force is pushing the student or pulling the student toward the center of the circle with 1,924 newtons of force. Number 3, what force keeps the student from sliding to the floor? Now let's draw a picture. Here's our student against the wall as it's spinning in the direction kind of like that. If I draw a free body diagram from the side, we have weight down, normal force from the wall, and we must have force of friction. So what keeps a student from sliding to the floor? It must be the force of friction. How do you get a big force of friction? Remember, force of friction is mu times the normal force, so you must have a big normal force, and that's what's causing the centripetal force is the normal force. So, force of friction keeps the student from sliding. What is the minimum coefficient of friction between the student and the wall required to keep the student from sliding down the wall? Well, in this case, in order to not slide down the wall, force of friction and the weight of the student have to be balanced. So force of friction must equal the weight of the student. But we just said force of friction is mu times the normal force. So mu times the normal force must equal mg, which implies then that mu must equal mg over the normal force. But we also know for all of this to work that the normal force is providing the centripetal force, which must be equal to MAC. So we could write that mu equals mg over MAC, which is just g over the centripetal acceleration, or 10 over, our centripetal acceleration was 29.6, and we find that we have a mu of 0.34. That's the coefficient of friction that we need in order to keep the student from sliding down the wall. All right, hopefully that's a pretty good refresher or fundamentals on uniform circular motion. Thanks so much for joining us at Educator.com. Make it a great day, everyone.